welcome to my lab. Are you ready to learn? Yeah! Are you ready to have some fun? Yeah! Well, let's get started then. In my lab, whenever we do experiments, we obey all the safety rules. I want everyone to notice that I have my goggles on, and I also want you to see that we have a fire extinguisher ready to be used just in case something goes out of control. We're not planning on anything going out of control, but we have it as a safety precaution, and it is really ready to be used, just like that. I'm going to put it right here where you and I know where it is in case it is needed. Obeying the safety rules is a must so that we enjoy the experiments that we do and we learn from them. I want you to see this book. This is a very colorful book. It's chemical demonstrations, and I wrote this book. You see my name is right down here, right? You see that, right? Right? So I want to open the book and just very quickly read the instructions for the next experiment. So bear with me as I do that, okay? Here, ooh. This is no ordinary book. This is a hot book. Actually, it's not a book at all. It's just the book covers. On the inside, there are two batteries. There is a filament from a light bulb, and there's a wick. I put some lighter fluid on the wick and soaked it before you came to my lab. There's one other thing I want to show you. At the bottom of this book, there is what looks like a small button. What color is it? Red. Right, red. Okay, so now I open the book and move it away from my face. Safety is paramount. When I push the button, the chemical energy that's stored in the batteries changes into electrical energy, and the filament lights up. Just like all filaments, all electric filaments of this type, when they light up, they give off electricity and they give off heat. And the heat ignites the fluid that I soaked the wick in. So you remember the fire triangle? You need three things to have a fire, right? You need something that burns, you need oxygen from the air, and then you need a source of ignition, usually heat, okay? So here we go. I move it away from my face, push the button, there, it comes on, okay? Now you tell me what happens when I close the book. What happened when I close the book? Just tell me out loud. No more oxygen. You know what? You're like the students in my class. They give a correct answer, but not to the question that I asked. The question, oh, you recognize that, huh? The question that I asked is, what happened when I closed the book? What happened when I closed the book? The fire went out. Why did the fire go out? Because there was no more oxygen, all right? All right, so I opened the book now. Is there oxygen or not? Yes. Yeah, but there's no fire. How come? We need three things to have a fire. What should I do? Just stop talking and push the button, right? That's what I should do, okay? But first, I move it away from my face, right? I push the button, there it is. We teach about the fire triangle, so we learn how to put out fires, not to start fires. All right? You like that experiment? Yeah. All right. Hello, Hina. Hinano, are you a student at the university?
Yes, I'm a student at University of Wisconsin, and I am studying music and business, and I also do science experiments.
Oh, you like science experiments. But,
I do.
But I see that you have your flute with you. Would you please play something more for us?
Sure. Could you get my music stand?
Of course.
I will be playing an arrangement of the Carmen.
Bravo. Bravo, Hinano. That was fabulous. That was really beautiful.
Thank you.
And now you said you'd like to do some experiments.
I do. I can show you some.
Right now?
Yeah, sure.
All right. Shall I follow you?
I have my safety goggles on and my gloves on.
All right. Very good.
So I have 6 solutions with me here. This blue solution is copper sulfate. I'm going to mix it with hydrochloric acid, and let's see what happens. This green solution is nickel sulfate. Let's mix it with dimethylglyoxime.
Very nice.
Not all solutions have to be colored solutions to create a colored solutions. This colorless solution is lead nitrate, and this colorless solution is potassium iodide.
That's beautiful, Hinano. That's not only beautiful, but very colorful.
Yes, and color can be also referred to in music with sound and tones. To help me show you this, I would like to invite Professor Mark Fink to join us.
Thank you, Hina. It's my pleasure to be here with you today. Normally, I play the oboe, a woodwind instrument, but today what I have with me is the oboe's big brother, the English horn. And the tone is produced with a reed, 2 pieces of wood that vibrate against each other to produce a sound. My reed isn't feeling too well today. Usually it sounds better when I put the reed on top of the instrument. You're a great audience. Hina, would you like to play something together to demonstrate
Sure.
our different colors of our instruments?
Let's play a duet, an excerpt from the William Tell Overture by Rossini.
Hinano Ishii and Professor Mark Fink. Thank you very much. Thank you. And this is an example of what we try to do in my lab. We promote creativity in science and the arts. We want to foster the connections between young people, older people, and try to develop talent so you can get to enjoy whatever your own interests are, whatever your own capabilities are in science, in the arts, and in the humanities. So once again, I invite you to take advantage, the young people in the audience, the parents, the neighbors, the grandparents, everyone. Take advantage of the great talent that we each have and put it to good use. All right? You promise? All right. Now I want to reach down here and get a magnetic stirrer. It has a light on it, so I'm going to turn the light. And I'm going to put on it a large beaker. This beaker is empty except for air, and this beaker has a volume of 4 liters. If you look at it right now, you just learned how big 4 liters is, and you cannot unlearn it. You may forget it. That's different. You think about that. I take a Teflon-coated magnet and put it in there and turn the switch on, and I'm going to use this to mix 3 clear and colorless liquids in the 4-liter beaker. Here are 2 of them, and here is the 3rd one. So I need to speed up this a little bit. I take the first liquid and I put it in. It's clear and colorless, but as soon as I put it in, you can see it's a little cloudy right now. And then I take the second one, add the second one. Anything interesting happened so far? Well, the volume increased, right? That's very common. And if I increase the speed, you can see what looks like a tornado. I hope this is the only tornado you will see up close. I take the 3rd liquid, and I add the 3rd liquid, and we see a color change and another color change. Oh, what? I don't see anything happening. How come I don't see anything happening? I'm not looking. What's the big deal about looking? The last time I looked at the beaker, the color of the liquid in the beaker was deep blue. Shall I look right now? I don't want to trip over anything, see? Every time I look at it, it's blue. You tell me when to look, all right? Tell me when to look. Shall I look right now? Right now? You're sure? I don't want to trip over anything. Maybe you can help me better on this side here. Tell me when to look, all right? Shall I look right now? Right this second. You sure? I don't want to trip over it. Right now? Every time I look, it's blue. What's going on here? I don't get it. I don't get it. Oh, wow. What is it that you were doing that I was not doing? You were looking all the time. I was looking all the time, but not over here. I was looking everywhere else. I was looking at you. When we do experiments, we have to pay attention. We have to be focused. We have to be learning from the different transformations that are taking place. This is an example of what we call a chemical oscillating reaction. It's one of about 50 known such reactions, but this one is very special to me. It's special for 2 reasons. One, it was discovered by 2 high school teachers, and it's named after them. It's called the Briggs-Rauscher reaction. Briggs and Rauscher taught high school chemistry and physics in Northern California. In 1973, they published a paper describing this beautiful, captivating behavior. A second reason it's special to me is that it took researchers, high-powered researchers, members of the National Academy of Sciences. It took them 9 years to figure out what's going on in here. So when we do scientific experiments, we pay attention, we're vigilant, and we try to understand what's going on. We always keep our patience. This has in it about 8 or 9 different chemicals: water, hydrogen peroxide, potassium iodate, malonic acid, sulfuric acid. It has potato starch. The yellow color is the color of iodine. Combines with the potato starch, it turns this deep blue, almost black color. This, ladies and gentlemen, is the Briggs-Rauscher oscillating chemical reaction. At this time, I would like you to welcome my longtime collaborator and friend, Dr. Rodney Schreiner. Rod?
Hello, Bassam.
Hello, Rodney.
It's a pleasure to be here on this 44th presentation, annual presentation. That's quite a record, isn't it?
I'm very proud of that, yes. Thank you, thank you.
You know, what we chemists like to do with anniversaries is to celebrate them using the element whose number corresponds to the anniversary. So we're today featuring element number 44.
Yes, element number 44, Ruthenium.
Element ruthenium.
That's the name of it.
Yes. And ruthenium is, like most elements, a metal. And like most metals, it's silvery gray in color. Looks kind of like iron and nickel and platinum. In fact, it's somewhat related to platinum. But rather than showing you an uninteresting gray lump of metal, I went and talked to a chemistry professor here in our department who works with ruthenium. His name is John Barry, and he gave me a bunch of ruthenium compounds, which I have here in this rack, solutions of those compounds. And you can see that ruthenium is a very colorful element. All sorts of colors, almost a whole rainbow of colors.
Very beautiful colors, yes. I like colors, you know that. And I like color changes, too.
Yes, well, speaking of color changes, I'd like to show you one that involves another metal, not ruthenium,
yes,
but vanadium.
All right.
So I'll set these aside and get my solution. Here's my solution of another metal, which is vanadium. And, you know, I was telling you about gray metals. Well, here I'll show you a gray metal. Here's another gray metal. It's zinc. Now, this is zinc metal. This is a compound of vanadium. All of the vanadium atoms in this solution have had 5 electrons removed from them. Don't worry about it if you're not a chemist. You don't need to know what that means exactly. But if we start adding electrons back to these vanadium atoms, something will happen to them. So first, I'm going to pour some of this yellow solution into that beaker, and then I'm going to mix the rest of it with the zinc, and the zinc is going to start putting electrons into the vanadium, and we'll see what happens.
So electrons transfer from the zinc to the vanadium.
Right.
One at a time, or what?
Sort of, well, let's see what happens. Already a color change has happened.
Right.
And that happened because the vanadium atom, each one, got 1 electron. So we went from missing 5 to missing 4. And if we mix it a little more, the zinc will transfer some more electrons. And now we've got missing 3.
That's very pretty, Rod.
And maybe if I stir it some more, we can get it to go to 4.
I see more color change.
It's changing. You know what? One of the virtues that chemistry teaches you is patience. Sometimes you need to wait for the good things to happen. And it looks like it's still happening here.
Oh, that's pretty also.
Yes, it keeps going. I think, yes, this is looking familiar.
Yes.
And there.
Beautiful display of color, Rodney. Thank you.
Isn't that pretty? Isn't that pretty? Thank you. Well, I've been working with another metal. This is actually a metal. It's iron. I have an iron pipe. And you know you can make sounds with metals. One of them, you can make it simply by tapping the metal. Some musical instruments are made of pieces of metal. Or you can make sounds by blowing air through a piece of metal. Some musical instruments are made that way too.
Okay.
Okay, it's not beautiful. But there's another way I can move air through this tube. If I put hot air at the bottom, the hot air is less dense than the cold air, and it will rise through the tube, so I don't actually have to blow it through. So what I'm going to ask you to do is help me get some really hot air here. There we go, and we're going to put it in the bottom of the tube. And you can hear sort of a noise, but the torch is making a lot of noise, so what I'm going to do is I'll take it away. Cool. And while I was doing this in the lab, I discovered something. Did you know you can pour sound? Let me show you. Here's a cup, my pipe. Let's make some more sound. Okay, I think. You can't see the sound. There it is. That's what happens when you can't see it. I ran out. I must be spilling it all over the place. I suppose you want to know how that works.
Yeah, I would like to know, and they would like to know how it works,
Okay.
yes.
There's something about this pipe that I didn't tell you earlier, in that at one end there is a small metal screen, a very coarse metal screen. Let's see if I can aim it there. Maybe you can see it inside. There's a coarse screen. When I hold that over the flame, the screen gets really hot. When I take it away from the flame, that hot screen heats the air. The hot air rises, drawing cold air through the bottom, and the cold air goes through the screen, and it whistles through that screen as it goes, and it starts to reverberate in the pipe. And when the screen cools off, then it stops making noise. Let me demonstrate again.
All right.
Of course you want to see it again, right? Now it requires the hot air to rise through the pipe. If I turn the pipe horizontal, it doesn't rise. It can't get through. But if I return it to vertical, then it can rise through again. This has nothing to do with it.
Thank you very much, Rod.
Thank you.
Here is a green liquid. Here's an orange liquid. And I have a blue liquid. And I also have a small beaker with a little bit of a yellowish, lightly yellowish liquid. And what I'm going to do is we now express to you my thanks and all the thanks from the people in my lab for your being such a wonderful audience. Here's our grand finale for you. Here's one. And here's another one. And here is the third one. Thank you all very much. Thank you. Thank you. And no matter what you do, remember, always remember, science is fun. Thank you all very much. Thank you again.